Hi everyone. In the last lecture, we have discussed some important properties of compact operators. Namely, we have discussed about the countability of the point spectrum of a compact operator. Today, we are going to show that even the approximate point spectrum of a compact operator is countable, and from that we can conclude that the spectrum of the compact operator is countable. So, let us start with a theorem. Okay, let T be a compact operator, then we can say that spectrum of T is countable. Let us look at the proof of this one. First, let us take that lambda to be an element in the approximate point spectrum. Let us take lambda in the approximate point spectrum of T and lambda non-zero. Now, by the definition of approximate point spectrum, T minus lambda is not bounded below, hence there exists a sequence xn in the unit sphere of H such that norm of T xn minus lambda xn converges to 0 as n tends to infinity. So, from this we can conclude that T xn minus lambda xn converges to 0 as n tends to infinity. We know that xn is a bounded sequence and T is compact. So, by the property of T, Txn must have a convergent subsequence. So, as T is compact, there exists a subsequence xnk of xn such that Txnk is convergent. Now, we know that Txn minus lambda xn goes to 0, hence Txnk minus lambda xnk also goes to 0, and we also know that Txnk is convergent. So, from these two observations we can conclude that lambda xnk is convergent, hence xnk is convergent because lambda is non-zero. So, this implies there exists some x in H such that xnk converges to x. So, from this we can conclude that now Txnk converges to Tx and lambda xnk converges to lambda x. So, by star, let me write this as star. Tx equal to lambda x. Now, we know that norm xnk is 1 and norm xnk converges to norm x, hence norm x is 1. So, we get that because norm xnk converges to norm x, that means x is non-zero. So, x is an eigenvector corresponding to lambda. So, therefore, we can say that lambda is in the point spectrum of T. So, what we have shown so far is that, so the conclusion, if you look at non-zero approximate point spectrum of T, that is part of point spectrum of T. But we know that point spectrum is always subset of approximate point spectrum. Now, we also know that we have already shown this part. Recall that the boundary of the spectrum is part of the approximate point spectrum. Okay. Now, we also know that point spectrum is countable. So we can use point spectrum of T is countable when T is compact. So from this observation and the earlier observation that we have made here, from this we can conclude that approximate point spectrum is countable. Therefore, approximate point spectrum is countable. Now, spectrum of T is compact and boundary of the spectrum of T is countable because it is subset of approximate point spectrum. Hence, we can conclude that spectrum of T is exactly the boundary of spectrum of T, and this is again part of approximate point spectrum. So, therefore, we can say that spectrum of T and approximate point spectrum of T both are same, hence we can say that spectrum of T is countable. Okay. Now, summarizing all these results, we can state the following theorem, which is due to Rees. Let us take T to be compact operator. Of course, T is non-zero. Then we have spectrum of T is countable and 0 is in the spectrum, and here H is also infinite dimensional space. Okay. And the second statement is 0 is the only possible limit point for the spectrum of T. 0 can be the only possible limit point of spectrum of T, and we also have shown that null space of T minus lambda I is finite dimensional for all lambda in the spectrum of T, lambda non-zero. In fact, we have shown that this is true for every lambda in C, because when lambda is outside the spectrum, it is invertible. T minus lambda is invertible. So, null space of T minus lambda is 0 in that case. Hence, the third statement is true even for set of all lambda in C where lambda non-zero. Okay. So, this is a summary of the results that we have proved in today's class and earlier classes. Okay. Now, as a consequence of this result, so we can actually show that the spectrum of T is exactly point spectrum of T union 0, because if dimension of H is infinite, then 0 is the only possible limit point for the spectrum, and non-zero spectrum is exactly the point spectrum. So, 0 is the limit point of set of all eigenvalues of the spectrum. Let us take lambda to be a complex number which is non-zero. Let us also take that T to be compact. Then lambda can be in the spectrum of T or in the resolvent set of T. So, either lambda is in the spectrum of T or lambda is in the resolvent set of T. When lambda is in the resolvent set of T, T minus lambda is invertible. But when lambda is in the spectrum of T, we know that So, if lambda is in the spectrum of T, then this is nothing but spectrum of T union 0, but we know that lambda is non-zero, then we can say that lambda is in the point spectrum of T. That means we can say that null space of T minus lambda I is non-zero, or there exists non-zero x in H such that Tx equal to lambda x. So, what we have shown is that if lambda is non-zero and lambda is in the spectrum, then lambda must be in the point spectrum of T, then lambda must be an eigenvalue. That means there exists a x such that Tx equal to lambda x. That means the equation Tx equal to lambda x has a solution. Now, let us look at the other case. If lambda is in the resolvent set of T, then T minus lambda I inverse exists and inverse is bounded. Hence, if you look at this operator equation, T minus lambda I at x equal to y, where y is in H, has a unique solution, because T minus lambda is invertible. Namely, x is nothing but T minus lambda inverse y. When any y in H, T minus lambda I at x equal to y has a unique solution. That means when we take a non-zero lambda and if T is a compact operator, then there are two options. One is this equation as a non-trivial solution, and the second option is T minus lambda I at x equal to y has a unique solution for given y. So, this result is known as Fredholm alternative theorem. So, let us write this. Okay. Let T be a compact operator and lambda is a complex number which is non-zero. Then the first is either Tx equal to lambda x has a non-zero solution, or the operator equation Tx minus lambda x equal to y has a unique solution for each y in H. When y is fixed, then there exists a x such that Tx minus lambda x equal to y, and the solution exists for every y. That means depending on y you get x. Okay, this theorem is known as Fredholm alternative theorem. Next, based on this, we prove one more important result, namely the Weyl's theorem. Which is an application of the Fredholm alternative theorem. So, let us take T to be a bounded operator. Let T be a bounded operator and K to be compact. Then we can say that the spectrum of T plus K is contained in spectrum of T union the point spectrum of T plus K. that is the eigen set of all eigenvalues of t plus k. Okay. So, let us take lambda in the spectrum of t plus k and lambda does not belong to spectrum of t. Then we want to show that lambda is in the point spectrum of t plus k. Let lambda is in spectrum of t plus k and lambda does not belong to spectrum of t. Then we know that t minus lambda I inverse exists and it is a bounded operator. So, let us consider the operator t plus k minus lambda I. Because lambda is coming from spectrum of t plus k, this operator is not invertible, but we can write this as t minus lambda I plus k. So, again we can write this as t minus lambda I plus t minus lambda I multiplied by its inverse multiplied by the operator k. So, this is nothing but, if you take t minus lambda I common, you will get I plus t minus lambda I whole inverse k. Now, the left hand side operator, so this is not invertible. So, from this we can conclude that this operator is not invertible. If this is invertible, then we know that t minus lambda is invertible. So, their product is invertible, that means the left hand side operator must be invertible, that is a contradiction. So, this implies I plus t minus lambda I whole inverse k is not invertible. And we also know that this whole operator is compact, because it is a multiplication of a bounded operator with compact operator. So, that product is compact. Now, this operator is of the form I plus k, I plus some compact operator. So, this implies this is not invertible, means minus 1 is not, minus 1 is in the spectrum of t minus lambda I whole inverse k, but by the Fredholm alternative theorem, minus 1 must be in the point spectrum of this compact operator t minus lambda I whole inverse k. This is by the Fredholm alternative theorem. Okay. That means null space of I plus t minus lambda I whole inverse k, this is non-zero. But we can easily show that this can be shown to be equal to the null space of the operator that we have started with, t plus k minus lambda I plus k minus lambda I. You can easily show, because left hand side is not invertible and t minus lambda is invertible operator. So, the right hand operator, right hand side operator I plus t minus lambda I whole inverse k. So, null space of that is exactly null space of t plus k minus lambda I, which can be checked very easily. So, that means this is also non-zero. So, from this we can conclude that lambda is in the point spectrum of t plus k. This is what we wanted to show, because we have taken lambda is not inside the spectrum of t. So, we wanted to show that lambda is in the point spectrum of t plus k. Okay. Next, we want to look at one more important property of compact operators. It is a characterization of compact operators, which depends on the weak convergence. So, we have studied earlier that weak convergence and weak star convergence for a nonlinear space. So, let H be Hilbert space. And Xn be a sequence in H, then we can say that xn converges to x weakly if and only if inner product xn with y converges to inner product x with y for every y in H. This directly follows from the definition of weak convergence. We know that xn converges to x weakly if and only if f of xn converges to f of x for every f in H star. This is the definition of weak convergence. We have discussed this earlier when we discussed about commutative C-star algebras. But by the Ries representation theorem, every functional is given by inner product. So from this we can show that this is if and only if inner product xn with z converges to inner product x with z for every z in H. And one more important observation is that in a Hilbert space xn converges to x weakly if and only if xn converges to x in the weak star topology, because xn can be identified as a functional on the dual space H star. So from that we can and using the canonical embedding we can conclude that the weak and weak star convergences are same. Okay. Now we want to characterize compact operator using the weak convergence. Next we prove a theorem. Let T be a bounded operator defined on H, then the following are equivalent. T is compact if and only if xn is a sequence in H such that xn converges to x weakly, then xn converges to txn converges to tx strongly. That means a compact operator maps weakly convergent sequences into strongly convergent sequences. Okay. Let us prove 1 implies 2. Let us take T to be a compact operator and xn is a sequence in H such that xn converges to x weakly. We want to show that txn converges to tx. Suppose txn does not converge to tx as n tends to infinity, then we can find then there exists an epsilon and a subsequence xnk of xn such that norm of txnk minus tx is bigger than epsilon. Okay. Now xnk is a bounded sequence. So as xnk is bounded and T is compact, by definition of compactness there exists a subsequence xnkl of xnk such that txnkl converges to y in H. Okay. Now xn kl is subsequence of xn k and xn k is subsequence of xn. So, note that xn kl converges to x weakly because the original sequence converges to x weakly. So, as t is bounded, we have t xn kl converges to t x weakly. Now, t xn kl converges to y implies t xn kl converges to y weakly. So, from that we can conclude that from this 1 and 2 we can conclude that 1 and 2 we get y equal to t x. That means t xn kl converges to t x. Now, but this contradicts star. Because norm of t xn k minus t x is bigger than epsilon. Now, t xn kl is a subsequence of t xn k which is convergent. This contradicts star. So, therefore, our assumption that t xn does not converge to t x is wrong. So, we can say that t xn converges to t x strongly. Okay. This proves 1 implies 2. Now, let us look at 2 implies 1. Proof of suppose 2 holds. That means T maps every weakly convergent sequence into strongly convergent sequence. You want to show that T is compact. So, to show that T is compact, let us start with a bounded sequence. Let xn be a bounded sequence. Now, we know that in Hilbert space every bounded sequence has a weakly convergent subsequence. So, there exists weakly convergent subsequence xn k of xn, that is xn k converges to x weakly. Let us say the limit is okay, but we know that by the hypothesis t xn k converges to t x by the hypothesis. Now, we started with a bounded sequence xn and we have shown that it has a subsequent xn k such that t xn k converges to t x, but this is nothing but T is compact. Hence, okay. That means this is one of the characterization of compact operators, that T is compact if and only if it maps weakly convergent sequences into strongly convergent sequences. So, let us look at one simple examples for this result. Let us take H to be the Hilbert space L2 and En be the standard orthogonal basis of L2. Then we can easily show that En converges to 0 weakly. In fact, this is true for any orthonormal basis of orthonormal set of any Hilbert space. Okay. Now, let us define d from L2 into L2 by d of En is 1 by n En for every n in n, and extend this operator to the whole space linearly. Then we know that D is compact. Now we can show that D of En converges to 0 strongly. We have D of En is nothing but 1 by n norm En, that is 1 by n goes to 0 as n tends to infinity. That means D of En converges to 0, that is nothing but D of 0 as n tends to infinity. We know that D is compact. Okay. So these are some of the important properties of compact operators. In the next class we will be discussing about spectral theorem for self-adjoint operators by dropping the compactness. I will stop here. Thank you very much.